Good evening, good day, everyone. Great to see you all. So, welcome to episode 24. And before we begin, a big thank you to all of you for helping this channel go beyond 100,000 subscribers, 1 lakh subscribers. It's all thanks to you. I have seen lots of messages of congratulations. So, thank you so much to everyone. I'm sorry I can't respond to each one of you individually, but it's all thanks to you. We are doing great work together, and this channel is not about me, it's about you, which is why until now I have been taking your questions and answering these questions throughout these past 23 episodes. And now that I have a good understanding of what you people want to know, then in the future soon I'm going to start making more detailed and more elaborate videos about those topics. So this is all about you. It's about what you need to see, what you want to see, and what you want to hear about. So once again, thank you so much to everyone for supporting my work and for being together in this project. And thank you again for those of you who have become members. I really appreciate that. Memberships are open in case you weren't aware. So thank you to all of you who have supported me in that fashion. Thank you very much. So we talk about science and physics and technology and AI today. So I know that the most popular topic on this channel is history. I know that. But we have to understand that one of the major lessons of history is that science and technology is critical in taking any nation, any civilization forward. If you are not proficient in science and technology, if you don't have the scientific attitude and approach, then you basically can't progress. So that is why science and technology is very important. We all need to understand what it is. We need to all develop a scientific outlook. And that's why this session is also very important. So let's get into it with question number 1. So Kunal asks, why did the US government stop the Apollo program after 1972? And why are they not resuming it now, since technically they are more advanced now? So the space program, the Apollo program, all of that was part of the great space race of the 20th century. It is a technological competition that took place between the United States and the erstwhile USSR. And the USSR was the first nation to take a big stride in this matter by sending the first artificial satellite into orbit. I think it was in 1957, Sputnik 1. And they were also the first country to send a human being into Earth orbit, which was Yuri Gagarin, and the first woman, Valentina Tereshkova, etc. So the Soviets took the first big strides in space exploration, and the Americans were scared. They were really paranoid about this. They worried that the Soviets could put nukes in orbit and they could spy upon the Americans from just 100 kilometers overhead. So that's why the Americans decided to take this on in a massive manner. That's why they also launched their own space program. Eventually, they surpassed the achievements of the USSR. And one of the major achievements was the Apollo program, in which they sent several manned missions to the moon. You first had unmanned missions, then you had manned missions. The first manned mission was simply an orbital mission. It went around the moon and came back. And then you had lunar landings. The first person was Neil Armstrong, etc. So the real purpose of this was to achieve first parity with the USSR and then to surpass the technological achievements of the USSR. And there's always a military background to any space program, there's always a military undercurrent. So that is the reason why they also were afraid that the USSR could set up bases on the moon and claim the whole territory of the moon for themselves. That's why they embarked upon this program, because the Soviets also had plans to send humans to the moon. So these two nations were neck and neck throughout most of the 20th century, second half of the 20th century. It was a race for not just technological supremacy, but military supremacy. And once the Americans went far ahead of the USSR, especially in the moon program, that's when it became apparent that the Soviets were most likely not going to take their own moon program further. And that's why the Americans did not see any point in continuing with that further beyond the early 1970s. And that's why the last moon landing was in the 1970s, after which they never tried to go back until now. Now what's going on is that there is a new moon race. There's a new moon rush. We know that the moon is rich in various resources, various minerals. There is a great deal of water there, and there is this there is helium-10 in abundance in the lunar soil, in the regolith of the moon, and this is a very promising future nuclear fuel. So this is one of the major reasons why the Chinese are going back to the moon. The Americans are planning to send human beings back to the moon. Even India is involved to some extent in this moon race. We were supposed to land the Chandrayaan lander on the moon's surface near the South Pole a couple of years ago. Did not exactly work out as we planned. So the Chandrayaan 3 program, the Chandrayaan 3 mission is supposed to happen sometime in the coming future. Let's see when it is. So the Americans are definitely going back to the moon in a very, very serious manner this time. There is a concerted rush to go back to the moon. The Chinese currently are ahead of the US in terms of the number of landers they are sending to the moon, especially on the far side of the moon. There's at least one mission operational right now, a Chinese mission, at least one. So the Americans are sending people to the moon in the next 2 or 3 years, back to the moon. So that's what the status is right now. We are at the cusp. We are at the beginning of a new rush to the moon and a new space race, because now the technology has advanced a great deal from the 1970s, and now we can actually start exploiting. Humanity can now actually start exploiting space and its resources in a commercial manner. So we're gonna see the privatization of space. Elon Musk and Jeff Bezos are competing for supremacy in space. Right now, SpaceX is ahead, but Blue Origin is not very far behind. So that's what's going on. We may soon start to see the privatization of space too. So it's essential that India gets involved in a big way in this. I hope that some plans hopefully are afoot. Okay, what's my view? What is my view on the Panspermia theory? What is Panspermia? Panspermia is the idea that that life basically originates in space itself. It is the hypothesis that microscopic life is present in large quantities in interstellar space, in basically on space dust, on comets, on asteroids. And life can even be transmitted through spacecraft, microscopic life. If you have microorganisms that humans, because we know that there are microorganisms on our skin. Now, if we are constructing a spacecraft, it will be handled with human hands, right? And then if you send it to the moon or to Mars, those microbes, those microorganisms from Earth will end up on Mars. So there is another means by which microorganisms can go across planets. So this can happen through spacecraft. It is believed that according to this hypothesis, it is believed that such microscopic life occurs across the universe, across galaxies. And we know that there are certain microorganisms on the Earth, such as tardigrades, for example, the so-called water bears, that are almost indestructible. They can survive the vacuum of space. And therefore, there could be other such organisms as well, extremophiles. So This is the hypothesis, panspermia, that life actually is seeded through these, uh, through either cometary impacts or asteroid impacts or just via space dust. And maybe the seeds for life, these microscopic seeds for life, they may occur across the universe. So it is a hypothesis. It hasn't been proved, but well, it's certainly a viable hypothesis because we do find evidence uh, of organic hydrocarbons, complex organic hydrocarbons, even amino acids on meteors, on meteorites. And if you look at the spectral composition of comets, you see that there is uh, carbon chemistry there as well. So it is definitely a viable hypothesis. There is no proof for it thus far, but it's definitely possible. We've even found a Mars rock that seems to contain fossilized microorganisms. It's not been proven conclusively, but it does look tantalizingly like the fossilized remains of a microorganism, of a bacterium of some kind. So it's definitely possible that space rocks from Mars could have reached the Earth in the early phase of the solar system. And if there was life on Mars, it could have been transferred to the Earth. And maybe there was life even before our solar system came into existence. And that was present in the uh, building blocks of our solar system. So these are all possibilities. There is no proof thus far, but it's definitely a viable theory. And maybe our DNA came from somewhere else. Even that is a possibility. So it's a hypothesis. It's not been proven, but it's definitely scientifically valid. So as of today, we don't have any evidence for it, but we are searching for it. If we actually find some microorganisms on a comet or an asteroid or elsewhere, then it would definitely bolster this hypothesis and make it more likely or more probable. Okay, what happens to the matters, the contents of a neutron star after it collides and gets destroyed with another neutron star? Because as we know, matter is neither created nor destroyed. Yes, you're right. There is conservation of mass and energy in the universe. So what happens when two neutron stars collide? So it depends on the total mass of these two neutron stars. First of all, these are extraordinarily compact objects. You have the mass of the entire sun within a diameter of about 10 kilometers. So that's extraordinarily compact. These are the densest objects in the universe apart from black holes. So that's what neutron stars are. Now, the maximum neutron star mass is defined by the Tolman-Oppenheimer-Volkoff limit, which says that a neutron star has between 1.5 to about 3 solar masses. I think the average, or the yeah, approximately the average, it's not a very definite limit, but the it seems that the upper limit is up to 3, most likely 2.2 or 2.3 solar masses. And beyond that, if a neutron star has more mass than that, then it becomes a black hole. So when two neutron stars collide, first of all, there's going to be a cataclysmic collision, and a great deal of energy will be radiated out in the form of gravitational waves and light. And some matter will be ejected out of this collision. So what happens is that a great deal of heavy elements are created when two neutron stars collide. For example, in a large star, more than 25 times the solar mass, you have these core collapse supernovas. And this supernova happens when the star starts trying to fuse iron at its core. And iron is basically nuclear ash. You can't fuse iron. Stars cannot fuse iron. And that's why they undergo these supernovas. So the heaviest element that a star can create is essentially iron. But we know that there are heavier elements in the universe. You have gold, for example. You have uranium and various other heavier elements. So how are these elements synthesized? And the answer is they are synthesized in neutron star collisions. So these neutron star collisions throw out a lot of ejecta and debris, and these are in the form of extremely heavy elements like gold and uranium and thorium and other elements. So that's what happens. But the resultant neutron star that is formed after the collision, is it a neutron star? Is it something else? That's the question. And that depends on this limit, the Tolman-Oppenheimer-Volkov limit. So if the resultant object has a mass of greater than around 3 solar masses, then it becomes a black hole. Otherwise, it becomes a larger neutron star. So that is what happens when two neutron stars collide. Now that's a very energetic collision, and it produces an intense flash of radiation in various frequencies and spectra. If it happens near the Earth, it can blind you, basically. That's how energetic the light output is. So that, in short, is what happens during and after a neutron star collision. Akash asks, is there any difference between the Big Bang theory and the cosmic inflation theory? That's an interesting question. So, one second. Here we go. Let me share a screen. Okay, so this here is essentially the timeline of the universe. So what is the Big Bang theory? It is not a theory of the origin of the universe. It is essentially a model of the history of the universe. It starts with the Big Bang. We don't know what caused the Big Bang, but it's about what happened after the Big Bang, right? So according to this theory, and this is the best theory that we have thus far, it is the most detailed theory that we have, and it explains a lot about the universe. So it's our best theory thus far. So according to this theory, in the beginning, you had the Big Bang, the initial singularity, which is a point of infinite density and mass energy. And it expanded. It was not an explosion, it was an expansion. And about 10 raised to minus 34 or 35 or thereabouts seconds after the initial expansion, you had something called inflation. So this was superluminal inflation. And it lasted just about 10 raised to minus 36 or 35 seconds. And the universe expanded by a factor of about 10 raised to 26 times. So that is a ridiculous, humongous amount of inflation in such a short, incredibly short period of time. And that is what gives the universe the properties that it has today: homogeneity, isotropy, etc., flatness, and all that. So cosmic inflation is essentially part of the Big Bang theory, right? It is the very initial, almost the very initial phase of the universe's history that we actually understand. We don't really know. We don't understand the physics of the very early universe before this cosmic inflation actually happened. We know there were quantum fluctuations that got dispersed out into space, and you had most likely primordial microscopic black holes produced in abundance before inflation and even after inflation. And these most likely formed the seeds of galaxies, the seeds of the supermassive black holes that you have at the center of galaxies, and all that. So that is all part of the Big Bang theory. And cosmic inflation is also part of the Big Bang theory. It's part of Big Bang cosmology, right? And this inflation is supposed to being triggered off by a hypothetical field called the inflaton. And so that, in brief, is about inflation or cosmic inflation, which is very much part of the Big Bang model of cosmology, which is the best theory that we have thus far. So this is one, and this is another example, another way of looking at the history of the universe. In the beginning, at 0 seconds, you have the Big Bang. And before 10 raised to minus 32 seconds elapse, the universe has undergone this massive spurt of inflation in which it enlarges, it becomes larger by 10 raised to 26 or 27 times, which is incredible. And before inflation, you had quantum fluctuations, which got dispersed all over. And then you have these different phases. You have nucleosynthesis, you have protons, nucleosynthesis, etc. And eventually, you end up with the universe that we have today. The first light is at around 380,000 years after the initial expansion of the universe, the Big Bang expansion, and so on. So this is the best theory, the best model of the history of the universe that we have as of today. And it all starts after the Big Bang with cosmic inflation. And this expansion of the universe is still going on, but at a much slower rate. So I hope that answers the question. Okay, Shri Ganesh asks. So this is about something I'd said in an earlier episode about the fact that ISRO is so badly underfunded. We have the best scientists in the world, the most talented people in the world, and yet ISRO is not really, basically it's not developing any new technology right now. It's not developing reusable rockets, it's not developing boosters that can come back and return to earth on their own. It's not building heavier rockets. It's not looking into light sail technology. I mean, it's just like a commercial enterprise which launches satellites for various governments and private companies for a fee, and that's all it does. It's the PSLV and the GSLV. And the reason for this is that there is no ambition on the part of the political dispensation of India. Politicians have no scientific ambition, apparently, because we don't see any sign of it. And that's why they're not funding ISRO enough so that it can develop more newer technologies, larger, more powerful rockets, etc. For example, if you want to send a mission to the moon, you can't send a rocket that goes straight to the moon. You have to lift that spacecraft into orbit, and then you have to do a number of orbit raising maneuvers. It takes months to reach the moon. If you had a powerful enough rocket, you could reach the moon in what, 2-3 days, less than a week for sure. So that's the kind of limitations ISRO is hamstrung with. It's all about funding, and there's not enough funding to do all this, right? So the question is, if the government is unwilling to fund ISRO, can the people fund ISRO? How can we fund ISRO directly, etc.? So here's the point. Let's say we start a crowdfunding campaign, all of us together. Let's say we all donate 1,000 rupees each, and if it is 1 lakh of us, so that's 10 lakhs is 1 crore. So you may have 100 crores. No, 100 lakhs is 1 crore. So if each of us donates 1,000 rupees, we may be able to raise 10 crore rupees. Well, and even if it's not just 1 lakh of us, even if it's 1 crore of us, each giving 1,000 rupees, we can raise 100 crore rupees for ISRO. Now, how do we fund ISRO with that money? We're going to have to hand that money over to the administrators and bureaucrats who oversee and control the budget of ISRO, right? And then it's all in their hands. It's not like the government of India doesn't have money. They have the money, but all these scientific projects and programs in India are all run by bureaucrats who know nothing about science and who don't really care about anything except bureaucracy, right? So this budget will be, the allocation will be decided by the bureaucrats, and they may even shift the money elsewhere because they may decide that ISRO doesn't really need that sort of money. And all the projects have to be sanctioned by the bureaucrats who govern ISRO or DRDO or anything, right? So the real problem is not the scientists. The scientists are not in charge of the budget. They don't have the power to decide the budget. They don't have the power. It is the bureaucrats and the higher ups in the government who decide all these budgets and decide the allocation of funds and all that. So even if we raise some kind of money and hand it over to the government for ISRO, eventually it's going to go into the hands of these bureaucrats. And that, my friends, is the real problem in the governance of India, the bureaucrats. I am not saying they're all bad people. There are many nice people as well. Okay, there are many patriotic people, even in the bureaucracy, IAS, etc. And yet the system is built in such a manner that even if you are one patriotic person, you cannot do anything except what the system tells you. If you try and go against the system, you're going to be transferred 15 times in 10 years, and you're going to end up doing nothing. So that is the problem in India. We are stuck with this colonial era system, and the governments throughout the decades have done absolutely zero to try and reform the system. So today we have this young, energetic nation. We have teenagers, we have 20-year-olds, and all of you guys want to see massive change. You want to see massive progress. You want to see the nation unleashed, the energy unleashed. And it is these colonial systems that are holding you back. The entire government is designed like this. The moment you try and interface with the government, the moment you approach any government organization or organ, you know how it feels. It's like time has stopped. So that is the system. That is what we need to see change. So even if we raise money for ISRO, it's going to end up in the hands of the bureaucrats, and then God alone knows what happens with it. Unfortunately, that is where we are today, 70 plus years after independence. It's still like we are in 1947, unfortunately. Okay. How do doctors assume the amount of memory loss in case there is a memory loss somewhere? And also, how, like memory is stored as JPEGs or GIFs, how is human memory stored? What an interesting question. So when a doctor, a neurologist, etc., says that a particular individual or person is suffering from memory loss, they cannot quantify the memory loss. Neuroscience is a very imprecise science, right? It's very vague. There's a lot of voodoo and hand waving to it. You can't determine. First of all, we don't understand the brain. We don't understand how it works. We have a rough understanding of what goes on in which part of the brain, little bit, but it's very rudimentary, our understanding, and we don't know where human memory is stored precisely. If I see something new today, where are those associations stored within the brain? In what form are they stored? We know that it's most likely the associations between different neurons that cause uh, the storage of memory. But how do we recollect smells and sounds and things like that in such vivid detail in some cases, right? And where does consciousness emerge from? Certain scientists tell you that consciousness and emotions are all chemical reactions that go on in the brain, but they are unable to give even a basic fundamental theory of how it happens. So the brain is an enormous mystery. The consciousness is an enormous mystery. How is memory stored? We don't know. For example, in JPEGs or GIF files, these are static files. So the memory is stored in a static manner. You can basically see it in terms of zeros and ones if you have the software for that. In the human mind, there are no zeros and ones. It's very different. It's very complex. So we don't know how memory is stored. It's probably the associations between the trillions of neurons and dendrites and all that in the human brain that probably causes the storage of memory, but we don't know how. So neuroscience, psychology, psychiatry, these are very well, there's a lot of pseudoscience in there. There's a lot of hand waving and voodoo in there. There is very little real understanding of how things happen. Yeah, sure, neuroscientists are able to basically operate on the brain and maybe rectify some problems, remove tumors, etc. And yet there's a lot. It's like dark matter and dark energy. We understand 5% of the universe, and we don't understand 95% of the universe. It's all unknown to us. Similarly, the human psyche, the human mind, the human brain, consciousness, all that, it's also, most of it is basically completely unknown to us. We don't know how it works. So that's where we are in science. This thing right on top of our eyes, on our heads, that itself we don't really understand how it works. It is the most complex object that we know of in the entire universe, and it's a vast mystery. Dungar Singh Chauhan asks, the moon is moving away from the earth at about an inch every year. Does it prove the fact that human life on earth will disappear when the moon will have no impact on earth, and menstrual cycles of women on earth will stop? As a result, humanity will end. I've been asking this for the 3 live sessions. Okay, so this solar system is about 4.6 billion years old. The Earth Moon system is roughly 4.5 billion years old. So when the Earth Moon system was formed, it is hypothesized that there was a giant impact of another planet on the Earth, and the material that was ejected out into orbit went into orbit around the Earth. It coalesced in the form of the moon. And there is some evidence that supports this theory. So when the moon was first formed, it was much closer to the Earth than it is today. In fact, the length of the day on the Earth, the rotation period, was about 4 or 5 hours. And the period of the moon around the Earth was also 4 or 5 hours. And then it's been receding away from the Earth at a certain speed, at a certain rate. Right now, it's about 2.5 or about 3 centimeters per second. It's the rate at which human nails grow. Hmm? So, at this rate, it's going to take billions of years for the moon to recede far, any significant distance away from the Earth. Now, the history of humanity is about a million or 2 million years in age. That's how old humanity is. I think the human chimpanzee split happened about 2 million years ago. And even those humans that split off from the chimpanzees were very ancient humans, archaic humans. The earliest known evidence of modern humans, modern, anatomically modern Homo sapiens, is about 250,000 years. Well, 250,000 years or even 2 billion years is an eye blink of time in the cosmological scale of in the yeah in the cosmological scale. It's nothing. So even in the next 2 million years, the moon will not have receded any significant distance away from the Earth to have any real change, to have any real effect on the way the world functions, the Earth Moon system functions. And the question is, will humanity last another 2 million years? 2 million, that's 20 lakh. Will it last that long? Or will we leave this planet and go away somewhere else? So these are questions, right? So the time scales that we are talking about are so vast that humanity is too small to even envisage that. We have been around for 2 million years at most, right? Some people believe that Indian history is 8 lakh years old or 30 lakh years old or whatever. So that is the kind of thinking that we need to address. So that's a different topic, but it's in a way similar to this uh, idea we are contemplating right now. So the time it will take for the moon to move away a significant distance and change the amount of time, the length of the day on the Earth, etc., is gonna be in the scale in the realm of tens or hundreds of millions of years. So it is not perceptible to humanity, and therefore it's not going to make any difference. By the time, humanity will also have evolved a great deal if it is still around that long on this planet, right? And by the time the moon reaches the furthest distance away from Earth, it's going to be another 50 billion years or so, by which time the sun won't even exist. So therefore, these questions are, the time scales that we are talking about are too vast to even worry about or take seriously, because it's too long. It's longer than the current age of the universe, right? So it really doesn't matter for us. Okay, Akash asks, what is the Oort cloud? Okay, A, why does it exist? B, how big is it? C, does it exist around every solar system? And D, could it have helped in evolving life in our solar system? So let me give you a visual idea of what the Oort cloud is. Let me share an image. Okay, this is a rough model of the solar system. So here, if you can see my mouse pointer, that's the sun. Here is the Earth. So this distance between the sun and the Earth is called 1 astronomical unit. So this graph is on the logarithmic scale. So this is 1 astronomical unit. This is another 10 astronomical units. 10. So this is the distance between the sun and the Saturn. This is 100 astronomical units. That's where the Voyager 1 spacecraft is roughly around right now. So that is basically where the solar system ends. That's the beginning of interstellar space. And the Oort cloud is a hypothetical spherical cloud of basically icy objects that are the nuclei of future comets. So that is what the Oort cloud is. It is an enormous cloud. Let me show you a different image. Okay, so let's take a look at this. So if you look at this image here, the red orbit here is that of Mars, the green one is Earth. This diffuse orbit over here is the asteroid belt, and the orange orbit here is the orbit of Jupiter. If you look at it here, it's very small, the orbit of Jupiter, and the purple one is the orbit of Pluto. And you have the Kuiper belt over here. And this red dot is the minor planet called Sedna, which is currently around 90 astronomical units from the sun. One astronomical unit is the Earth-Sun distance. Here you have the orbit of Sedna, which is an enormously elongated orbit. Yeah. So it tells you how small the orbit of Pluto is in comparison. Let me remove that, right? So that gives you an idea of the orbit of Sedna. And this is the orbit of Sedna in comparison with the Oort cloud. So that gives you an idea of how large the Oort cloud is and how far away it is from us. It's essentially in interstellar space, but it is still under the influence of the sun's gravity. It's an enormous cloud, hypothetical enormous cloud of cometary nuclei, the nuclei of comets. Now, what happens is that if this Oort cloud does exist, and there is a good chance that it does exist, so if this Oort cloud does exist, then it is only loosely influenced by the sun's gravity because it is so far away from the sun. It's essentially in interstellar space. And it is also affected by the gravitational attraction of nearby stars, passing stars, and also the gravitational attraction of the Milky Way itself. And therefore, you see that from time to time, various cometary nuclei get dislodged from their orbits, and some of them are sent tumbling towards the sun. And that's what eventually becomes comets. So this is basically a hypothetical reservoir of comets. So it's almost halfway to the nearest star. That's what the Oort cloud is. So it's hypothetical, but there's a very good chance that it does exist. And it exists because of the way the early solar system formed. The solar system formed from a primordial cloud of gas that was left behind from the death of another star. So the solar system is a reincarnation of a previous solar system, and the material that was left behind after the circumstellar disk coalesced into the sun and the planets, that became the Oort cloud. Initially, it is believed that it was much closer to the sun, and eventually it drifted out further away from the solar system, from the sun, because of the gravitational interactions of the gas giant planets. Okay, so it's quite far now. It's in interstellar space. It's very, very large, but it's very diffuse. Does it exist around every solar system? There's a good chance that it exists around many stellar systems. We haven't really seen, because it's such a small, diffuse. It's not small, it's very large, but it's very diffuse, and the cometary nuclei therein are very, very small. So it's almost impossible to detect around other stars and even around our own solar system, which is why it's still hypothetical. But if it exists around our solar system, there's a good chance it exists around other solar systems as well. Could it have helped in evolving life in our solar system? Well, we spoke about panspermia, this theory that microscopic life exists across the galaxy on dust grains and comets and asteroids, etc. So if some of these cometary nuclei did contain the seeds of life, then it could have seeded life on the Earth in the very early solar system when the Earth was under intense bombardment from comets and asteroids. So there is a possibility that it may have played a role in the seeding of life in the early Earth. Akriti asks, which way to look at gravity is more profound? Is Einstein's way, in which space-time fabric is a four-dimensional thing, or is it the exchange particle concept of gravitons? Which one is correct? Well, we know that general relativity, which looks upon space-time as a four-dimensional fabric, it is a stage upon which or within which the universe plays out. So that definitely, it is the best theory of gravitation that we have as of today. It is a very accurate theory. All of its predictions thus far have been proven to be correct, and it is being tested all the time, and it is the most accurate theory that we have thus far. So Einstein's view the four-dimensional space-time fabric is definitely correct, but it is not completely correct, because we know that there are uh, certain scales at which it breaks down. For example, we are unable to quantize curved space-time, four-dimensional space-time. We are unable to do it. Quantum field theory is not compatible with general relativity, and we have these singularities that this theory throws up in the form of what happens within the hypothetical black holes. Space and time, the curvature becomes infinite, the mass energy density also becomes infinite. This is an indication that the theory breaks down at the quantum level, at the ultra microscopic level. So there's definitely a better theory out there somewhere. We still haven't figured it out. And one of the ways we are looking to do this is to quantize gravity, to have a quantum theory of gravity in which the hypothetical graviton will be the mediator of this force. It will be the exchange particle. Let me share this image. So this is the standard model of physics. This is the best theory of particle physics that we have, the best theory that describes the 5% of the universe that we can actually see. So you have these three generations of matter: the quarks, the leptons, and the gauge bosons. You have 6 quarks. You have the leptons, electron, muon, tau, lepton, and the corresponding neutrinos. Then you have the gluon, which is the exchange particle for the strong nuclear force. You have the photon, which does it for electromagnetism. And you have the W and Z bosons, that are the gauge bosons for the weak nuclear force. And then you have the Higgs boson, that imparts mass to various particles and which is responsible for the mass of the universe. Now, if the graviton concept is correct, then you would have one more 18th particle here, which would be the graviton, which would be the gauge boson for the quantum theory of gravitation, for quantum gravity. Well, thus far we have seen no evidence that this actually is correct. The graviton is a hypothetical spin zero particle boson. So this thus far has not been proven. It is far from being proven. So the best theory that we have as of today is Einstein's general relativity, four-dimensional space-time. But there could be a better theory out there, and that's what we are seeking. So maybe gravitons do exist, but we are very far from seeing any experimental evidence of gravitons, and very far from formulating a proper theory, a coherent, consistent theory of quantum gravity. Sujit asks, can you please tell us about the newly found third type of supernova? You have been asking many questions from the past 3 sessions. I hope you are okay. So here we are. So let's first talk about the first 2 types of supernova. There's the type 1 supernova and the type 2 supernova. So let's talk about type 2 first, which is strange, but let's talk about that first. So the type 2 supernova is when you have a star. So first, let's talk about our own sun. Will our own sun go supernova? It won't. It is too small to undergo a supernova explosion. So our sun basically contains about 73% hydrogen, 25% helium, and then some other traces of other heavier elements. And the nuclear energy, the nuclear reaction within the sun is the fusion of hydrogen into helium. So that is what drives drives the sun. Now, after the hydrogen is used up, most of it, the sun will fuse helium into a heavier element, and the sun doesn't have enough mass to fuse heavier elements than this. So once the hydrogen and helium fuel is used up, the sun will become a red supergiant, and eventually the outer layers will fly off into outer space, and what will be left behind will be a white dwarf, and that will be the end of the sun's existence as a star. That's how it will slowly cool down. Now, when you have a star that is between 10 to 25 solar masses, it is able to fuse heavier and heavier elements. So it goes on fusing heavier elements to create energy, fusion energy, until it reaches the element of iron. And iron basically, to fuse iron, it takes more energy than the fusion reaction is able to give out. So iron is basically nuclear ash, and once a star starts creating iron in its core, its lifetime can be measured in milliseconds. So once the iron is formed in the core of a star, which is between 10 to 25 solar masses, it within a fraction of a second, its energy output ceases, and this entirety of the star, all the outer layers, enormous outer layers that are being pushed out and held up by this by the energy of the fusion reaction, they all collapse onto the core of the star. And they collapse onto the core of the star and then they bounce out, and that is a supernova explosion. And what's left behind at the core is a neutron star. So this is called a type 2 supernova. If a star is heavier than 25 solar masses, you won't have a neutron star which will form at the center. It will be a black hole. Now, if you have a star, now what is a type 1 supernova? A type 1 supernova is a strange supernova in which you have a large star and a neutron star and a white dwarf. That are orbiting each other. So it's a binary star system, two stars, a regular star, and a white dwarf. So let me show you what this looks like. Hang on. Let me make this. Yeah, here you are. So you have a regular star here, if you can see the image. And it has a companion star, which is a white dwarf, a small one. And in this system, the white dwarf star is stealing material from its companion star. Okay, so this is that type of system, a binary system, two stars in which the white dwarf is stealing material slowly from its companion star. Now, there is something called the Chandrasekhar limit, which is 1.4 solar masses, which is as big as a white dwarf can get. Now, this white dwarf is stealing material from its companion star, so it's getting larger. Once it reaches the Chandrasekhar limit and exceeds the limit, it essentially vaporizes in an enormous explosion. And that is called a type 1 or type 1a supernova. It's also called a standard candle because we know exactly how much luminosity it will have. So this is a type 1 supernova. A white dwarf detonates and destroys its companion star in the process. That's a type 1 supernova. Now we have a third type of supernova, which has been hypothesized, but it seems to have been discovered recently. So this is a star which is between 8 to 10 solar masses. Now, a star is basically when it is basically held up by electron degeneracy pressure, which is a quantum effect in which electrons don't want to be too close together, so they push against the star's exterior, and that's what holds the star into this in this shape. Now, when certain nuclear reactions happen, so basically, I'll tell you about quantum degeneracy, what it is. All the matter that we see, it is able to have a certain shape because of quantum degeneracy pressure. So that is a quantum effect which gives the universe and the world that we see the shape it is. It's what makes matter solid. It is not electrostatic repulsion, it is quantum degeneracy pressure that gives solidity to matter. So it is a quantum effect that we actually see in real life, even though we don't realize it. So this electron degeneracy pressure basically pushes back against the outer layers of the star, which want to fall back inside. But in this type of star, between 8 and 10 solar masses, at a certain stage, what you have is that you have electron capture, a nuclear reaction that starts happening, in which certain heavy elements start capturing electrons, and these electrons fuse with protons and produce neutrons. So suddenly this electron degeneracy pressure, which is holding the star up, it vanishes and the star implodes and then explodes. So there is a third type of supernova that has recently most likely been discovered. It's called an electron capture supernova. So it seems that we have finally detected this type of supernova. I'm not sure what is left behind at the end of this thing. Is a white dwarf left behind? Is something else left behind? I think it's still a matter of conjecture, but this is what it is, the type 3 supernova, an electron capture supernova. Amruta asks, does the revolution of our solar system around the Milky Way have any effect on the Earth's atmosphere or life? That's an interesting question. So the solar system, the sun, does revolve around the center of our galaxy, the Milky Way. So one such revolution can be looked upon as a galactic year. and one galactic year is about 230 million years. So every 230 million years, the sun makes one revolution around the center of our galaxy. That's one galactic year. So by that measure, the sun is about 20 galactic years old. It's quite young. So does it have any effect on the Earth's atmosphere and life? Not really, not to any extent that we can measure, because the galaxy, the neighborhood of the galaxy that we live in, it also revolves in that manner around the galactic center. So it doesn't really have much of an effect on our solar system. The amount of gravity that we feel from our parent galaxy is the same. The stellar neighborhood and other stars around us are more or less the same. So it doesn't really affect us to any uh, significant or measurable extent. It's just one measure of the lifespan of a star. So from where the sun is, it takes about 20 galactic years. It's about 20 galactic years old with that measure in mind. Prajwal asks, can a person having no technical background enter in the field of AI, artificial intelligence? Is programming and coding essential for AI? What can be a roadmap for a beginner having no tech background to make a career in AI? See, in any scientific field, you need to know math. And so mathematics is the foundation of all sciences, unless you want to go into biology or something, which is basically a soft science. In any hard science like physics or chemistry or computer science, you're going to need mathematics, and you will need to be quite good at mathematics. So that is the price for entry. That is the price you have to pay to enter into this field. The first thing is mathematics. So you need to learn basically differential equations, linear algebra, and all that, which would need you to first learn algebra, geometry, college level calculus, and then move further ahead depending on how deep you want to go into it. So there's a definite learning curve into this. And secondly, you need to learn programming, coding. It is a prerequisite for doing any significant work in the field of machine learning or artificial intelligence, neural networks, any of that. So first you need to learn mathematics if you want to do real research in AI. And secondly, even if you don't really learn mathematics that well, you need to know coding, programming. That is a prerequisite. It is non-negotiable. Without that, you just can't do anything in AI. So that's what I would suggest. If what is a roadmap? Well, start learning math. You can learn math online for free, and start learning a programming language. I think one of the best programming languages out there for any beginner is Python. You can learn it entirely for free. If you have a computer or a laptop, you can check out various courses on YouTube or other places where you can learn the whole thing in great detail for completely free. And you can download free tools that will allow you to start doing the coding and all that. So you can learn everything for free today. So I would suggest you should do that if you're really interested in this. Aryan asks, what does the statement, I need to add X dimensions to make my theory work, mean? And secondly, in one episode of the Ranveer show, I heard you say that all the technology we use today is based on quantum mechanics. Can you explain how? So what does it mean when you say that I need to add more dimensions, X dimensions, to make my theory work? So let's say you have a theory and you're trying to see more patterns in this theory. So for example, there is something called Kaluza-Klein theory, in which you are able to see more patterns if you add one extra dimension in space. So the mathematics becomes different. Every physical theory, every theory in physics is a mathematical theory. It's all constructed using mathematics. And it's so you assume 3 dimensions and you play all the mathematical equations, you see how they evolve and what they give you, and that is a mathematical theory in 3 dimensions. Now you can add an extra dimension to this theory and see how it looks. So Kaluza-Klein theory is a theory in 4 dimensions that shows us more patterns or symmetries between, for example, gravity and electromagnetism. And when it comes to string theory, in which they try to construct a theory of the universe, a model of the universe built upon the existence of one-dimensional strings, then they find that 3 or 4 dimensions simply do not give you the the supersymmetries that we see in space-time and all that. So mathematically, they are forced to add either 6 or 7 dimensions to this theory in order to get a coherent mathematical theory of the universe. So if you add 6 dimensions, you end up with 10 total dimensions in addition to space and time. And if you add 7 dimensions to it, you end up with an 11-dimensional string theory. So string theory is basically, well, it's not a theory, it's a hypothesis, because it doesn't really give you any testable predictions thus far. But that's what it is. So it's basically, you're trying to game the mathematics and try to see if it throws out any theory that actually makes sense in the physical world, in the physical domain. So essentially, you're tweaking the math by adding or subtracting dimensions and seeing what fits best. So that's what it means, roughly, tentatively, by saying that I need to add extra dimensions to my theory to make it work. Okay, the second part of the question. I said that most of the technology we use today is based on quantum mechanics. Yeah, can I explain how? Yeah, that's a good question. So we don't realize it, but almost everything that we use today is based on quantum technology, on the practical uses of quantum mechanics. For example, transistors and microchips and microconductors, they are all based on quantum mechanical effects. Microprocessors, USB drives, solid state drives, the sensors that you have in smartphone cameras and DSLR cameras, all of these are based on quantum mechanical effects, which means that computers won't work without quantum mechanics, and smartphones won't work without quantum mechanics and quantum technologies, which essentially tells us that the entire computer and smartphone industry is dependent on technologies that are based in quantum mechanical effects. Then you have lasers and LEDs and fiber optics. So fiber optics are basically classical. These are classical objects. These are long fibers through which laser pulses are passed, and that is again all about quantum mechanics. So these are governed by the laws of quantum mechanics. So the entire telecommunications industry is based upon quantum mechanics. We would not be having this conversation right now, this telecast right now, if fiber optic technology did not exist, and that is based on quantum mechanics. So this, what we are doing right now, would be impossible if we had not discovered quantum mechanics and if we had not learned how to use that in technology, right? So making phone calls is because of quantum mechanics. Scanning groceries in a supermarket, you have these laser scanners, that's again quantum mechanics. Then you have GPS. So GPS, when your phone picks up a GPS signal and tells you where you are, how does it happen? You have this constellation of satellites in space, these GPS satellites. These satellites, they're basically transmitting a very accurate transmission of the time. They have these atomic clocks on them, each of these satellites. These atomic clocks are very accurate counters of time. It is based on the transition between quantum states of either cesium or rubidium atoms. So your phone basically gets a signal of the time, what time it is, from a number of different satellites, GPS satellites, and it does some mathematical calculations, how much time it took for this signal to come from which satellite. And based on that, it's able to triangulate your location on the planet. So it's all possible because of the quantum transitions between rubidium and cesium atoms that these atomic clocks measure and then transmit via the satellite. So that's again quantum technology. Then you have electron microscopes, you have magnetic resonance imaging, or NMR imaging, nuclear magnetic resonance, which is based on quantum spin. You have PET scans, position emission tomography, which is again a quantum effect. So I could go on and on. But as you can see, all of these technologies, this entire vast bouquet of technologies that we take for granted today, they are all based upon quantum mechanical effects. If we had not discovered quantum mechanics, if we had not developed the technologies based upon this theory, then none of this would have been possible. So that's what I meant by saying that almost all the technology we use today is based upon quantum mechanics. Okay, Akash asks, what is plasma? How does it look and feel like? As the sun is made of plasma, correlated to this, does the sun have a surface where we can hypothetically stand? And what about the gas giants? So plasma can be considered to be the fourth state of matter. You have solid state, liquid state, and gas state. Plasma is a fourth state. So what is a plasma? Plasma also is a gas, but it is a ionized and charged gas. So you have a gas in which the gas molecules have been stripped of their electrons. So these are ionized molecules or ionized atoms, whatever, right? And so you have a gas of these charged particles, ions, and free electrons. So that's what the gas is made of. So in the case of the sun, you have mostly hydrogen and helium. So the solar plasma is made up of protons, which are hydrogen nuclei, alpha particles, which are helium nuclei, and free electrons. So that is the solar plasma. So that is what plasma is. It is basically ionized gas made up of ions and free electrons. It is electrically conductive, right? It conducts electricity. It is very strongly affected by magnetism. So you can create plasmas on the earth. Plasma TVs, etc., they use this technology of creating plasma. Now, when it comes to the sun, does the sun have a surface? The sun has layers. The overall density of the sun is greater than the density of water. So if you would place the sun in a hypothetical ocean made of water, the sun would sink below it because the sun is denser than water. Now, when you come close to the sun's core, you get densities that are in excess of 100 times the density of water, which is basically much denser than the human body. So yeah, if you could withstand the heat of the sun and you were to plunge into the atmosphere of the sun, eventually you will reach a place where the sun's density is greater than your density, so you will just float there, right? Because of buoyancy. So there you will reach a place, a layer in the sun where you would just float up and down, bob up and down. So it's not a surface, it's a layer, a level in the sun where the density exceeds the density of the human body, if the human body can ever withstand that sort of temperature, right? And you can say the same about gas giants. So for example, Jupiter, its outer atmosphere is just gas. As you go towards the core, towards the center of Jupiter, the density of the gas of this planet starts increasing. It goes on increasing. Even the temperature goes on increasing. It gets really hot inside. And a certain depth below the surface of Jupiter, you will reach a density where the density exceeds that of the human body, and therefore you will just float there or bob there. So that's about Jupiter, or Saturn as well, or Uranus or Neptune. They all have increasing density as you go towards the interior. So I hope that answers this question. Excuse me, 1 second. Okay, Divyansh asks, can you talk about the TRAPPIST-1 exoplanet, which is said to be in the habitable zone? How do we decide whether a planet is in the habitable zone from here? Does being in the habitable zone imply the existence of life in that region? Okay, what is the TRAPPIST-1 system? So the TRAPPIST-1 star is a red dwarf star. It's about 40 light years from where we are, from the sun, from the Earth. It's a very small red giant star. Its diameter is just slightly larger than the diameter of Jupiter, but its mass is significantly more than that of Jupiter, which is why it is a star, which is why there's a fusion reaction going on inside it. It's a very small star. It's a very cool star compared to the sun or other stars, and it's a dim star. Now, what is the habitable zone? The habitable zone is the region around a star where liquid water can exist. So it's neither too close to the star where water would evaporate, nor is it too far from the star where water would freeze. It is that region around a star where water can exist as a liquid. So it depends on from star to star. Some stars are very hot, so it would have been the habitable zone would be further away. Some stars are cooler, then the habitable zone is closer. So in the case of the TRAPPIST-1 planet star, it would be much closer than what it is in our solar system. So the Earth and Venus and Mars most likely are within the habitable zone in our solar system, because this is the region where liquid water can exist. So I think there are about 7 exoplanets that have been discovered around the TRAPPIST-1 star, and I think these are terrestrial type planets, rocky planets, and I believe there are at least 3 of these exoplanets that are in the habitable zone around this star, and at least one seems to be very Earth-like, which would indicate perhaps that there is a possibility of a liquid ocean on it, which could indicate a chemistry that is similar to that of the Earth. So maybe there is life there. Maybe. So being in the habitable zone does not imply or guarantee the existence of life. It just says that there could be life there similar to the kind of life that you find on the Earth. So the TRAPPIST-1 system is very interesting because you have so many Earth-like planets there, and also because you have at least 3 planets that are in the habitable zone. So there is a possibility that there could be Earth-like conditions there on at least one of these planets, and maybe there could even be the possibility of some form of life there. So it's very interesting. Okay, why can't we engineers make India's own Google with the help of great professors in IITs and students' collaboration? I am thinking about it. I'm glad that you are thinking about this. Well, how do you make a Google? First of all, you need a good idea. You need you need all the infrastructure. You need to. A good idea is not enough. You need investments. You need funds. You need angel investors to recognize the fact that you have a good idea, and then they need to invest in you and in your work and give you the means and the funds and the resources needed to take your idea to the next level. That's how Google was. Well, that's how Google was built. 2 students came up with this idea of semantic search, and then they took it forward, and they were desperately short of cash. They needed cash for building an array of computers that could hold all this data, and they needed a lot of funds for that, and they got lucky that angel investors invested in them, and they kept on getting more investments, and that's how this giant company was founded. That was the genesis of the company that eventually became this global giant. In India, we don't have the angel investment ecosystem, right? We don't have a Silicon Valley kind of place where there will be so many investors and there will be all these engineers who can interact with each other and get ideas from each other and all that. And in India, the laws and the system is such that it is very non-conducive to entrepreneurship. The moment you start doing good, there'll be all kinds of extra fees that you will have to pay to various politicians, etc. Any entrepreneur knows this in this country. Convenience fees or whatever you call them, So the entire system is basically set up against entrepreneurship. That's why you have all these companies like Flipkart, etc., that are based outside of India. They operate in India, but they are based out of India because they do not want to be subjected to all these problems that entrepreneurs and companies face in India. And that's why India simply doesn't develop, right? Because we have all the talent, but the system is loaded against any company like that succeeding. When it comes to the IITs, well, who told you there are great professors in the IITs? I'm not saying they're all bad professors. Maybe 10% of the professors in the IIT are good or great, but I would not say that most of the professors in the IITs are great. All right. And look at the way the IITs are. Go to any IIT, okay? You will find that there are crores of rupees of investments in the IITs, in the auditoriums, and in the washrooms. You have 1 crore rupee washrooms, very well built, very luxurious. Even the auditoriums are very luxurious. But when you go to the lab, you will see that the equipment is at least 20, 30 years old. It's obsolete. So the people who are running the IITs and managing the budgets and the funds, they are funding auditoriums and washrooms and all that. And they are not funding the technology. They are not allowing the IITs to have the latest cutting edge technology. Everything is 20 to 30 years old. And the attitude of most of the professors Well, it's like they don't want any progress. Unfortunately, I have to say this. I think anybody who has tried to do research or a PhD in any IIT knows this. This is what they all face. So it's basically we are breeding mediocrity over there in all the IITs to the greatest extent. There are definitely some shining stars among the professors, but those are few and far between. Overall, you have the reservation system, which is basically the opposite of meritocracy. You may get less marks in the entrance exam, but because of reservations and all of that, you are still given admission to the IITs and all. And the same goes for the appointments of professors and all that. So what the IITs once were, maybe 15 years ago, has been destroyed. The IITs were once in the top 10 around the world in technical institutions and research institutions in science and technology. Today, they are nowhere in the top 100 even. So the quality in the IIT is terrible. Most of the professors are mediocre. The equipment is obsolete, and the people who are funding and running the IITs have the wrong ideas. They are constructing $1 million washrooms and $1 million auditoriums and neglecting the actual purpose that the IITs were built for or meant for. And the students, you will see, the most of them are basically they are just trying to get a degree and get the hell out of India because there's no future here because of the way the system is. So that is a state of affairs in the IITs and overall in the Indian education system. Nothing is being done to redress this. Basically, we need to revamp the education system from the ground up, making some small changes, cosmetic changes here and there, and this new academic reform that was instituted last year. It's all a joke. It's pointless. It's worthless. So what is needed in India is the kind of education reforms that were done in China 30 years ago. It's still going on. China basically turned their entire education system around, especially in the science and R&D field. They completely revamped their education system. And that's why China is now beginning to lead the world when it comes to AI and quantum computing and superconducting computing and everything else. So we don't have great professors in the IITs to the most part. The students basically they want to leave. I mean, I don't understand why can't the IITs take the lead in, for example, in building supercomputers. India has maybe 2 or 3 supercomputers in the top 100 supercomputers in the world. Why can't you have an annual competition in the IITs between all the IITs of constructing the most powerful supercomputer? Why can't we do that and give the team that wins a $10 million prize? They can use it as seed funding for starting a new venture. Why can't this sort of initiative be taken up? Why can't you have this sort of competition among the IITs, between the IITs every year? India will leapfrog all the other nations within just a few years if you have this sort of innovation happening in the IITs. Unfortunately, there is no initiative like this in the IITs. The professors, the administrators, nobody cares. So this is the reason why India is not doing well in science and technology. The system is designed in a manner that hampers any such progress. The system rewards mediocrity. And that is what needs to change. I am very positive about India. India has the best talent in the world, and we are seeding the world with our talent. We are exporting our best talent abroad. And they are the ones who are heading Microsoft and Google and whatnot today, right? So what if we were able to build a system in India that actually values this talent and rewards this talent? India would not immediately, within a decade, within a generation, India would become a superpower. So that is the job of the government. We can keep wishing, we can keep saying, but we don't have the power to change anything. We are not in charge of the administration of the IITs or the education system. We are not in charge of the budgets. Everything is in the hands of the government. It is for them to wake up from their slumber and do some reforms quickly. Aditya asks, will the evolution of AI lead to millions of jobless people? Good question. So AI will definitely eliminate lots of jobs. AI is all about automation. It's about efficiency. So automation will eliminate lots of manual jobs, and this is definitely going to affect the lesser developed countries the most. You can already see some of these effects in India. The emergence of these big online retailers like Amazon and Flipkart are cutting into the profits and the wages of these small shops, the small kirana shops and all, to a very great extent, right? So it's already happening, but when AI comes into real effect in full force, it's going to eliminate lots of jobs, lots of manual jobs and all. So yeah, so it's problematic when you have a system that is capitalistic in nature, where you will be paid only if you have a job. The dream of science fiction writers in the 50s and 60s and 70s was that with the advent of superior technology, the need to work will be eliminated, and the technology and the robots will do the job work for us, and human beings will be able to live a life of leisure. But the dystopian scenario we are facing today is that the capitalistic system is predicated upon making people work. And if you don't work, you have no income. If your job is eliminated by AI, then you become jobless. Then you become basically, you have no income. So you go below the poverty line and you have to depend on other people, and you become a burden on society. That is not the way it should be. That's why this system, which comes from the West, is a very, well, it's not the right system for the world. I am not advocating communism or Marxism or socialism. We need a different system in which people don't need to work a certain hours of day in order certain hours per day in order to get a certain wage. One of the solutions people are giving is UBI, Universal Basic Income. Well, that is one possibility. We need to come up with better solutions. But as of today, with the increasing uh, emergence of technology and the increasing ubiquity of technology in our daily lives, and because of artificial intelligence, machine learning, automation, all that, you will definitely see millions of job losses, especially in less technologically advanced societies such as India. In Africa, you will see a lot of stress on these societies going forward. So that is something the government needs to start thinking very seriously about and doing something about. Paras asks, what do you think about the concept of superdeterminism? That everything that happens in the universe is predetermined. Interesting question. So, in physics, in the laws of physics, if you know the state of a system at a certain initial time, then you can determine the state of the system at a future time. You can determine how the system evolves over time at every step of the way until a future time, or until any time in the future. So the laws of physics are deterministic. If you know the initial conditions, you can calculate the future conditions. Maybe 10 seconds down the line, maybe 3,000 seconds down the line, maybe 10 million years down the line. You can calculate if you have enough computing power. Now, when the Big Bang happened, when the initial singularity expanded and gave birth to the universe that we are in today, you had a set of initial conditions. There was a very large number of variables, but with a large enough computer, you can actually calculate the initial conditions, and you can actually calculate the future conditions at any given point in time in the future, maybe 13.8 billion years later. So if you have a powerful enough computer, given the initial conditions of the Big Bang, you calculate and compute where the universe would be precisely 13.8 billion years later. So this would indicate that everything that's happening in the universe was predetermined at the time the universe was born, which would indicate that what we are doing right now was all predetermined, which would indicate there is no free will, that everything that we think that we are thinking or we are making choices is actually being predetermined at the birth of the universe. So this theory is called superdeterminism. It is a theory. There's no proof for it. Maybe there can be no proof of it, but it is one of the theories that resolves the paradoxes of quantum mechanics. because we are told that quantum mechanics is extremely strange. It is counterintuitive. You have spooky action at a distance, quantum entanglement, all that. But if superdeterminism is true, then all of these problems go away. All the randomness also goes away. So it is one of the possible solutions to the paradoxes and inconsistencies of quantum mechanics. So basically, it says that everything is based upon differential equations, and whatever quantum randomness exists or occurs in the world is purely statistically random. There is no free will in it. We cannot will that randomness into existence. So if this theory is correct, it means that the universe is a clockwork universe, and even we are simply clockwork components of it, and everything we are doing and will do in the future has already been predetermined in the past. So it's one of the interesting and somewhat scary theories in physics. Harsh asks, how exactly does gravitational lensing work? Is there a way for humans to recreate that effect with our technological means in the future? Or does it just happen at vast galactic scales? So gravitational lensing is the bending of light because of matter. In general relativity, in the four-dimensional fabric of space-time, the force that we perceive as gravity is basically the curvature of space-time, and space-time gets curved because of the presence of mass. So when space-time is curved because of mass, then a light beam can't pass straight through space-time. It also becomes curved. So this is one of the predictions of general relativity, that matter bends the path of light. And that is how we basically proved it, that general theory is indeed correct. For example, let me show you an image. So this here is a galaxy. It's an image of a galaxy that has been curved and warped by the presence of mass between us and that galaxy. So this circular thing is called an Einstein ring. It is a single object that has been distorted and warped because the light coming from it has to pass through this mass, central mass, so it becomes bent. And that's what causes the distortion in the image. Here's another way of looking at it. It's a black hole passing between us and a galaxy. We are the viewer. There is a galaxy over there, and there's a black hole that comes between us and the galaxy. And that's how it distorts the light coming from the galaxy. So basically, this is gravitational lensing. We can observe it at vast galactic scales. We can also observe it during a solar eclipse, when stars which are actually physically behind the sun become visible during a solar eclipse because the light is bent around the sun. So that is gravitational lensing. It is with the current technology that we have, we can't really produce the effect, but we can see it. There is no technology for gravitational lensing. It's just that mass will bend the path of light. So that's all it is. There is no real technological application of it thus far. Okay, Aditya asks, what is the speed of gravity at the event horizon of a black hole? That's an interesting question. So gravity has only one speed, and the speed at which gravitational effects propagate in the universe is the speed of light, which is the cosmic limit in the universe. So think about it this way. What if the sun were to suddenly disappear, which means it goes dark? Well, we will not know this sitting here on the earth for at least 8 minutes, because the time it takes for light from the sun to reach the earth is about 8 minutes and a little bit more. So if the sun were to go dark, we will come to know only 8 minutes later. And similarly, the gravitational effect of the disappearing of the sun would be apparent only 8 minutes later. So the speed of gravity across the universe is the speed of light. That is the speed at which gravitational effects or the ripples in space-time propagate. So the speed of gravity is the same wherever you are, whether it's at the edge of the event horizon of a black hole or at any distance away from a black hole. The speed of the gravitational effects is the same everywhere. It's the speed of light. All right, my friends, I am done with the pre-selected questions. Let me see some live questions. Some live questions. And thank you to all the new members. Thank you very much. Jatin asks, photon has wave as well as particle nature, wave particle duality. So how does it travel in space where there is no medium? As particles need medium to travel. Well, photons are localized concentrations of energy in the universal electromagnetic field. So the entire universe is permeated with fields. That is quantum field theory. There is no such thing as empty space. There is no such thing as vacuum. Space is teeming with, space is permeated with fields. So one of these fields is the electromagnetic field, and these photons are local concentrations of energy or local waves in this infinite electromagnetic field. So you have this medium in vacuum, this electromagnetic field, it's everywhere, and that's what photons are manifestations of. So photons basically travel in space in vacuum. Particles can travel in vacuum, definitely. So that's what it is. I hope that answers your question. They can be particles as well as waves. They are localized wave packets. So they are like particles, yes. And you can actually feel the radiation pressure. That's what that's what is behind the light sail technology. So the impact of photons on material actually exerts a radiation pressure. So that is the momentum that photons have. But they are also waves because they have a frequency and a wavelength. And they travel across space, across the universe, in the vacuum of space. They are manifestations of this infinite field, the electromagnetic field. Okay, good question. Why can't we Indians make jet engine technology if we can make a rocket engine? Well, it's a good question. Rocket engines are more powerful, but jet engines are more complicated. Hang on. So we have been making rocket engines since the 1970s at least. And yet we are trying to create a jet engine, the Kaveri jet engine, which is being under development for decades. First of all, the principal reason why the Kaveri jet engine has not succeeded thus far is because of political interference. When a foreign power gives a politician a bribe and says, buy my technology, don't develop your own technology, well, certain kinds of politicians will take that money and they will try and delay the indigenous technology development program. So, one of the main reasons why the Indian technology has been delayed thus far is because of political interference. That's why the LCA Tejas jet fighter was delayed for so many decades. And in recent times, it took off because there was no more political interference. There was political will for this program to come to fruition. And so that's one of the reasons why the jet engine technology is delayed. The second thing is that it's a very difficult and complicated technology. You have to build the jet engine turbine blades have to withstand enormous temperatures and pressures. So you basically have to build these jet engine blades out of a single crystal of metal. So that technology takes a long time to develop. You need to have a good R&D scientific ecosystem in the country in order to be able to develop the technology. And in India, well, we don't have that sort of ecosystem. The academic system is based upon rote memorization and teaching from textbooks. It is not based upon research. In the US, the entire academic system is heavily based on research in technology. And so the same goes for China. In India, we don't have it. The academic system basically doesn't do any real research. So these are some of the reasons why we have not been able to develop the jet engine technology thus far. I hope that changes. I think there is political will nowadays to some extent. So I hope it happens soon because we need that. Okay, let me take one more question. Let me take one more question if I can find one. How long do you think until the human brain can be reverse engineered and uploaded to another substrate like non-biological intelligence? I think it's very, very far from that stage. We don't understand the human brain. We don't understand how memory is stored. We don't understand how various patterns are stored. So until we understand that adequately, we can't transfer memories or even forget about consciousness. We can't even transfer memories properly to another storage system. So the key is in understanding how the brain works and how memories are formed and what gives rise to consciousness. Only then can we upload it somewhere else and create a duplicate copy of that. So that is still very, very far away. Reverse engineering the human brain is it's still very much firmly in the realm of science fiction. Okay, I get lots of questions about time travel. What do I think about time travel? Tushar asks. So I think that from the understanding of physics that we have thus far, it is most likely not possible, okay, based on the understanding of the laws of physics that we have thus far. There are many of these reports of time travelers coming from various from the future, etc., and giving us some information, etc. Well, it's never been confirmed, so one can think of it as an urban legend. None of it is confirmed, right? But from the understanding of physics that we have thus far, it appears that if time travel were possible, it would basically violate the causal structure of the universe. So it appears that it is unlikely, but it's still something that we are looking into. We are still researching it. Some solutions of the Einstein equations of general relativity may possibly make wormholes possible, traversable wormholes, in which case time travel may theoretically perhaps be possible, but maybe such wormholes can't be traversed. So it's going on. It's a matter of conjecture and debate, and the last word is not been spoken about this yet. But thus far, it looks like it most likely may not be possible. What is spooky action at a distance? Shirish asks. It is quantum entanglement. If you have a pair of entangled particles, let's say one particle has spin up and the other one has spin down. They are entangled together in what is known as quantum entanglement, and they are sent in opposite directions in space. And let's say after a few years, these two particles are 1 light year apart. And let's say one particle is with me, and I take a look at it, and I see it's spin up. Then I will instantaneously know that the other particle is spin down, even though it is 1 light year away from where I am. So it appears that this information from that other particle reaches me faster than the speed of light. So that is a very simplistic way of looking at quantum entanglement. And that is what Einstein called spooky action at a distance. So it's one of the paradoxes of quantum mechanics. It does seem to be faster than light, many times faster than light. So it's one of the mysteries of quantum mechanics. So that's what it is, spooky action at a distance. Okay, my friends, this is the end of today's session. Thank you so much for your questions. Thank you for watching, and I will see you in the next episode. Thank you so much. Have a good night. Have a good day wherever you are.